Hi everyone, welcome to our second video example related to our lecture on thermodynamic correlations. This example is question 8.61 from the textbook page 471. I have modified it just really slightly, not a whole lot. So go ahead and read up the question from the textbook and then follow along with this video example. Here we have an equimolar liquid mixture of N-pentane and N-hexane. We're given the temperature and pressure of this feed. It is fed into a flash evaporator at a rate of 100 moles per second. So the feed is exposed to the reduced pressure, which we don't know what the pressure is. We are supposed to find that. Some of that is going to be vaporized and some of that will remain as a liquid. The temperature in the evaporator is maintained at 65 degrees C by adding heat. And we have this vapor and liquid phases that are at equilibrium with each other, and we're going to discharge them as separate streams. We are also told the composition of our liquid product stream, which is 41 mole percent pentane. So part A is to draw a fully labeled diagram, do a degree of freedom analysis to make sure that you have enough information to solve this problem. And part B actually requires us to solve it, just the material balance part of things. So it's going to be a review of back in chapter 6 when we did vapor-liquid equilibrium. Part C is where it's new, where we're actually talking about the energy balance and the energy requirement, the Q, required to basically maintain this evaporator at 65 degrees C. So we want to know what is the rate of heat addition. I'm going to zip through part A and B really quickly. I'm going to show you the diagram and the degree of freedom analysis. There's a very similar example that we did back in chapter 6. So hopefully you're able to follow along. If not, go back to that example and refresh yourself on the material that was covered there. So here's the diagram. We have our evaporator. We are given every single information from our feed stream 1. We have the temperature and the pressure. We have the molar flow rate, and we know it's equimolar, so we know the molar compositions as well. We have a vapor in equilibrium with the liquid stream coming out. In the liquid stream, we are given the compositions of 41% pentane, so 59% is hexane. We do not know the molar flow rate there. In the vapor stream, we only know the temperature, we don't know the pressure, we don't know the composition, and we don't know the molar flow rates. In addition, we also have the Q, which is what we're trying to find in part C. So in this case, in our degree of freedom, we have 6 unknowns, which are circled in the diagram. In this case, we have 2 species, our pentane and our hexane. We have one constraint, the sum of our mole fractions have to sum up to 1 in our vapor stream. We have vapor-liquid equilibrium for 2 different species, our pentane and our hexane. So we have 2 different laws, Raoult's laws we can write for pentane and hexane. And lastly, to calculate our Q, we can write one energy balance. That will give us our degree of freedom of 0. So we're going to solve for our 6 unknowns using 2 balances, 1 constraint, 2 Raoult's laws, and 1 energy balance. In terms of the material balances, here's I'm just repeating the diagram and the DOF. We're going to start with Raoult's law. Here's Raoult's law. The left-hand side is related to the vapor stream, so the mole fraction of pentane in that vapor stream times the pressure is equals to the mole fraction in the liquid multiplied by its vapor pressure at 65 degrees C. We're going to use Antoine's equations to evaluate the vapor pressure at 65 degrees C. And so now we have our first equation, which has our 2 unknowns, the mole fraction of pentane and the pressure of the evaporator. We're going to solve that concurrently with our Raoult's law for hexane, which is going to look very similar, but now we're going to need to reevaluate our vapor pressure of hexane at 65 degrees C using the new Antoine's constants. And so we have this equation. We're going to solve these 2 equations concurrently together with our constraint. And the easiest way to do that is essentially recognizing that this is essentially just the partial pressure of pentane. This is the partial pressure of hexane. And if I sum up both of these, I can factor out the P naught, and I have my constraint. Or the other way to think about it is that when you sum up the individual partial pressures, you get the overall pressure of the system P naught. So I'm going to sum up 1 and 2, and I end up with my P naught of 1157 millimeters of mercury, or 1.52 atmospheres. Once I have that, I can put it back into any of the equations to find my mole fraction. So here's my mole fraction of pentane, and then use my constraint to find my mole fraction of hexane. So we have finished our Raoult's laws, we have finished our constraint. To finish solving our material balances, we're just left with our 2 balances. So let's start with our overall balance. Here we have in equals to out, so we have just N1, N2, and N3. Solve it concurrently with our pentane balance. And now you have 2 equations with 2 unknowns. Solve them simultaneously, and you end up with the mole molar flow rates for N2 and N3. So everything so far has been a review. We're just doing the material balance part. Now let's move on to what is new, which is our energy balance to find our Q. We're going to start with our overall, actually, before that, we actually need to answer the question, make sure to answer the question. In this case, it wants the volumetric flow rate of our vapor stream. And so we're just going to assume ideal gas in this case, use our ideal gas law. In this case, I've converted everything to SI units, so I know my volumetric flow rate is going to be SI units, which is meters cubed per second, and I can convert that to liters per second. After that, we also asked to find the fractional vaporization of pentane. Fractional vaporization of pentane is how much pentane came out in the vapor compared to how much was put in the feed. So how much came out in the vapor is YP2N2. How much was put in the feed is XP1N1. Putting all the numbers that we have already found, and we have 48% fractional vaporization. All right, now we are ready to go on to our energy balance to calculate our Q. We're going to start with our open system energy balance. So we're going to start from the general balance here. The same assumptions apply, so neglecting kinetic energy changes, potential energy changes, and in this case we have no shaft work. So our Q is just delta H, and now we get to expand out our delta H, which is the sum of all the outputs minus the sum of all the inputs. In this case, if you look at the diagram, you see that we have two output streams, a vapor stream and a liquid stream, and we have one input stream, which is our feed stream. So you might think that if we expand this out, we should have only 3 different terms, but actually we have 6. We are not exactly looking at the number of streams that are coming out of the evaporator, but the number of components that are within each stream. So when you look at each one of these terms, this is the specific enthalpy associated with one particular species. For example, in our vapor stream, we have 2 species, so we have a specific enthalpy of pentane and a specific enthalpy of hexane in that vapor stream alone, which means I'm going to have 2 terms from this stream, 2 terms from the liquid stream, and 2 terms from the feed stream. That gives us 6 different terms in this entire equation. So now let's start expanding it out slowly. I'm going to start with our stream 2, which is our vapor stream. So here you see in our vapor stream we have the molar flow rate of pentane multiplied by the specific enthalpy of pentane, which is the vapor at 65 degrees C. I will talk about that 1 atmosphere in a bit. Remember, before this we had solved our P0 as 1.52 atmospheres. This is actually the partial pressure of pentane, which I'll show you in a bit. So finishing up the vapor stream term, we also have our molar flow rate of our hexane multiplied by our specific enthalpy of hexane, which is a vapor phase at 65 degrees C and at the partial pressure of hexane. The way we calculate our partial pressures is just the mole fraction multiplied by the overall pressure. So we have already solved for all of those, and it turns out that the partial pressure of pentane is 1 atmosphere and the partial pressure of hexane is 0.52 atmospheres. So that's how I came up with those 2 pressures over there. So that is the 2 terms for the output stream 2. Let's write our 2 terms for our output stream 3, which is our liquid stream. So in this case, we have the molar flow rate of pentane in the liquid stream multiplied by the specific enthalpy of our liquid stream at that same temperature and pressure. Same thing with the hexane down here. So we have 4 different terms for the outputs, and now we have our feed stream. So we're going to subtract our liquid stream. Here's our molar flow rate of pentane, specific enthalpy of pentane, which is the liquid at 80 degrees C, and then here's that for our hexane. So those are the 6 different terms. We have already solved for all the mole fractions and molar flow rates. So all now we need to do is to figure out the enthalpies, the specific enthalpies of our hexane and pentane at the different states and at the different temperatures. But before we do that, we need to make sure that we have the same reference state for each of our terms for each species. So we need to pick a reference state for each species. Pentane and hexane does not need to have the same reference state. They can have different reference states because they are based on their species itself only. So I'm going to pick the reference state as my input stream. So my pentane is going to be liquid, 80 degrees C and 5 atmospheres. Same thing with hexane, liquid, 80 degrees C, 5 atmospheres. So those are going to be my reference state. The enthalpies at those points are going to be 0. So all I need to evaluate are the other 4 enthalpies. But before we do that, it is actually better to put everything in a table. It makes things look a lot nicer this way. So what I have down here is my pentane and hexane in my first column, in the liquid and vapor phases. And then here I have columns for my input stream and columns for my output stream. I have the molar flow rates and the enthalpies, molar flow rates and the enthalpies. So in this case, once I've figured out all my enthalpies and I put it into this table, my final Q is simply this multiplied by this, plus this multiplied by this, plus this multiplied by this, plus this multiplied by this, and then you subtract the sum of those two. So the table gives you a very nice way to just look at the values and how we can calculate Q in the end. What we need to do now is really to look up or figure out what this H1 to H4 is. Once we have that, we can put it into this table. So let's take a look at how we can do that. What we're trying to do here is calculate the specific enthalpies for the different streams coming out with respect to the reference state down here. So recall that we have picked the reference state for pentane and hexane as the reference state for the input, which is liquid 80 degrees C and 5 atmospheres. So I'm going to calculate it for pentane, and then I'm going to leave the hexane as sort of an exercise for you. I will give you the final solution for that. But in terms of pentane, let's look at the stream that's coming out, which is our H1. To do H1, what we are trying to do is we're going from a reference state of liquid 80 degrees C and 5 atmospheres. And what we are trying to get to in H1 is our pentane, which is also at liquid, 65 degrees C and 1 atmosphere. So this is the liquid stream that is coming out of the evaporator, and that's what we're trying to find. This is our H1 that we're trying to calculate down here. So in this case, what you see is that we have a liquid, we're changing the temperature, and we're changing the pressure. So we know H1 from our thermodynamic correlations that is both, because it's a liquid, we have both an effect of temperature and an effect of pressure. We know that the effect of pressure is V hat delta P for a liquid, and we know that the effect of temperature is the integral of Cp dt. And we are integrating from T1 to T2, so we are integrating from 80 degrees C to 65 degrees C. And so we're going to evaluate all of this. From here we can get the correlation from table B2. But before that, let's evaluate this V hat delta P down here. Remember that V hat is essentially 1 over your density. This is just 1 over density. So we need the density of our pentane. Where we will look up density of pentane, we can look up the specific gravity of pentane. So if you look up the specific gravity of pentane, you'll see that it is 0.63. And so all we need to do is multiply this by 1,000 to get it to kilograms per meter cubed. The other thing we're going to need eventually is our molecular weight of pentane. So I'm just going to write it down here for now, and later you'll see where it comes into play. This is 74 grams per mole. Okay, so let's evaluate our V hat delta P down here. I'm going to do everything in SI units. So our V hat is 1 over our density, so 1 over 630 kilograms per meter cube. This is from our specific gravity multiplied by 1,000 kilograms per meter cube, which is our reference density. Now our delta P down here, it is the final minus the initial, so we have 1 minus 5 atmospheres. But I'm going to do everything in SI units, so I'm going to convert atmospheres to pascals. All right, and so now I have this, and this is our V hat delta P term. So now let's do our integral term. Down here, if you look up the Cp, the constants, for a liquid, you actually only have A and B. I'm just going to skip the step and do the integration right away. And so you have, here's our A, and then our B, 43.68 times 10 to the power of minus 5. And this over 2 came from the fact that we integrated a t, it becomes t squared over 2. All right, and then we are going to evaluate this from 80 degrees C to 65 degrees C. All right, so we're going to do this math down here. From here, if we evaluate this term down here, you're going to end up with minus 643.3. In terms of the units, we know that this is some kind of specific enthalpy. So it has some energy per mole or energy per mass. Because this is a density, we know that this is going to be a density per energy per mass. So it's going to be, in SI units, will be joules per kilogram. But we are doing this entire problem in per mole basis. So we need to convert this joules per kilogram to joules per mole, and that's where the molecular weight is going to come in. We need to convert kilograms to moles, so we're going to multiply that by our molecular weight, which is 75 kilograms per kilomole, or 1,000 mole. And this is going to be our V hat delta P term. Down here, I can just do the math and actually use it because we're going to get joules per mole down here, or kilojoules per mole down here. And I can just use that right away. You have minus 2.986 kilojoules per mole. All right, evaluating this math down here, doing one more step, minus 0.048. So when I multiply this is going to be joules per mole, so I have to divide that by 1,000 again, and that's how I get 0.048 kilojoules per mole minus 2.986 kilojoules per mole. Now, I'm writing this out step by step because now you can see that the effect of pressure, even though you're decreasing from 5 atmosphere to 1 atmosphere, the effect of pressure compared to the effect of temperature is very, very small. So this value is much smaller than this value. In general, the effect of pressure is generally much smaller than that of the effect of temperature. So with that, we have minus 3.034 kilojoules per mole, and we have our H1. We need to repeat this for H2, H3, and H4. H2 is going to be exactly the same, except now we're going to have hexane, liquid 80 degrees C to hexane. And so the only difference is the specific gravity and molecular weights are going to be different, and the CP constants are going to be different, but the math is exactly the same. So what I'm going to do is I'm going to leave that as an exercise for you. I'm going to show you H3 actually, where now we actually have a phase change associated with it. For H3, what we are doing is going from our pentane reference state, so liquid 80 degrees C and 5 atmospheres. In this case, we're going to vapor 65 degrees C and 1 atmosphere. So this is our H3 that we are trying to calculate down here. Here we are changing both the state and the temperature and the pressure. So because of that, we actually have to create a hypothetical path for us to be able to calculate H3 down here. And that's simply because we have a change in state down here. So what we need to do is to first get this to our boiling point of our pentane, vaporize it, and then bring it back to the temperature and pressure that we want. In terms of the boiling point, again, you can look up the table in the back of the book. Our boiling points, in this case for pentane, is 36.07 degrees C. All right, so what we need to do is first bring this to liquid 36.07 degrees C and 1 atmosphere, because all of these values, the boiling points are given as a normal boiling point, which is at 1 atmosphere. So we're going to bring this down here, and we're going to call this step delta HA. From here, we can vaporize it. So this is our latent heat of vaporization. And then eventually we can bring it back up to the conditions that we want now that we have the correct state. And this is going to be delta HB. This delta HV, you can look up the table in the back of the book. And for our latent heat of vaporization of our pentane, we have 25.77 kilojoules per mole. Now what we need to do is to figure out delta HA and delta HB. Then we sum up the three of them to get our H3 down here. So let's start with our delta HA. In delta HA, we are in a liquid phase. We're changing both the temperature and the pressure. So it's going to look a lot like our H1, where we are at the liquid phase and changing both temperatures and pressures, which means we have a V hat delta P plus a Cp dt, in this case going from 80 degrees C to 36.07 degrees C. We have already looked up the specific gravity of our pentane, so we know This is 630 kilograms per meter cubed. Here we are again changing from 1 to 5, which is going to look almost identical to what we had before. Converting it to SI units. And from here, we are going to look at the CPDT. And again, this is the exact same constants that we had before, because we are talking about the same species and we're talking about the same state. So these are all the same. The only difference is we are integrating to a different temperature. So in this case, we are going from 80 to 36.07. All right, so this is all exactly the same. Remember that after we evaluated this is going to give us joules per kilogram. So after that, we still have to multiply that by the molecular weight first. So maybe I'll just put a note down here. You have to multiply by our molecular weight of 74 kilograms per kilomole. And once you have evaluated this, I'm just going to give you the numbers here. You have once again, you can see the difference in magnitude. This is due to the change in pressure. This is due to the change in temperature. And this is much, much greater than this. All right, from here, we have our delta HA. All right, that is just one step of it. We have finished our delta HA. Now we need to do our delta HB over here. So our delta HB, what are we going from? We are at a vapor phase. We are changing both. We are just changing the temperature without changing the pressure. But since we are in the vapor phase in general, we're just going to assume ideal gas anyway, which has no effect of pressure. So for a delta HB, all we have is the CPDT going from 36.07 degrees C to 65 degrees C, and just do the integration. In this case, when you look this up, remember that this correlation and these constants are for the liquid phase. Make sure to look for the correct line. In terms of the vapor phase, you have different constants. And so when you do this integration, what you have is this. The constants are going to look different, and you have more terms. So this is my A. My B is 34.09. And then 18.99. And 42.26. And we are integrating from 36.07 to 65 degrees C. Okay. I'm going to write out each number again so you can see, like I talked about, generally this term is going to be much larger than this term, larger than this term, and larger than this term. The higher order powers generally become more negligible. You have 3.321 plus 0.498 minus 0.014, 0.00017. All right, so now with this, you have your delta HB. We finish our delta HA, delta HB. We have our latent heat of vaporization. Now we can do the entire calculation to find H3, which is what we want. Right? H3 is delta HA plus our latent heat of vaporization plus our delta HB. So we have minus 7.988 plus 25.77 plus 3.805, and that gives us 21.587 kilojoules per kilomole, and that is our H3. So again, our H4 is going to look very similar in terms of the process, except now we are doing hexane. which means you have to use different CP values, different densities, different latent heats of vaporization, different boiling points. Go ahead and try that, and we'll continue with this example by putting in all the numbers for H1, H2, and H3 and H4. Now that we have calculated all our specific enthalpy values, I've put it back into this table, H1 to H4. And like I mentioned earlier, to calculate Q, we just have to sum up the multiplication of all this minus the inputs. So we can put in all the numbers down here, and we end up with 640 kilowatts. And that is the rate of heat addition that's needed for this process to actually happen. So that's all we have for this example. There are various ways you can double check whether you understand what's going on. The easiest way is actually just to pick different reference states. So in this case, you'll see that I've picked the reference states as my inputs. What you can do is to redo this entire example by picking our reference states maybe as our outputs for the liquid. You will end up with very different H values, but ultimately your Q value should come out to be the exact same thing. So it doesn't matter what reference state you pick. Or you could pick, for example, pentane, a reference state down here, and maybe a hexane for reference state down here. You could pick both vapor reference states down here. That will actually make your life really, really hard, because you're going to have to do a phase change for all 4 of your enthalpies that you're trying to change. But it'll be good practice for you as well. So go ahead and try that, work with different reference states, and make sure you end up with the same value of 640 kilowatts. That's all I have for this video example. Work hard, be smart. I will see you in the next lecture.